in the last few classes, we learnt about POS tagging and named entities in natural language processing. Now, if we are building a model using any statistical approach, what would be the best sequencing model that we can select? So, today's class we are going to see the sequencing modeling like hidden Markov model and maximum entropy Markov model and conditional random field. So, let's understand what is sequence modeling. It involves in predicting and labeling the sequence of text such as words in a sentence. So, common task includes especially part of speech tagging and named entity recognition. So, models here we are going to see, as I said, HMM, MEMM and CRF. Let's start with HMM. So, a hidden Markov model is used to model where we observe outputs but not the underlying states. Okay. So, in the context of POS tagging, there are something that we need to understand, because the hidden states are nothing but the sequence of POS tags. So, either N and VB are nothing but hidden states here. That is the one we are aiming to predict, and observable symbols are nothing but actual words in the sentence. Let's again take the sentence like secretariat is expected to raise tomorrow. Now, the goal is to assign the correct POS tag to each word. Now, here all the words are actually nothing but observed symbols, and POS tags are nothing but hidden states. Now, HMM helps us to determine the most likely sequence of POS tags given the sentence. How is it going to do? Now, it requires some kind of components. One is states. The states are hidden variables that influence the observed outcomes. For example, tags like noun, verb kind of thing, and observations that we know, the visible outcomes that are nothing but words. And there are two things, one is transition probability, another one is an emission probabilities. So, the transition probability is a probability of transitioning from one state to another state. For example, the probability of, let's say, VB in the given context of NN, here the probability of verb following a noun is being identified. And emission probability is an observation being generated from a state. So, for example, when you have probability of VB with the word race is nothing but, now we are identifying the probability of the word race being generated with the given tag VB, that is a verb. And another thing is initial state distribution. So, probability distribution over the initial states, when we do not have the other transition and emission probabilities, this initial state distribution is being used. For example, P of NN, the probability that the first word in a sentence is a noun, that is also being used. Now, what is hidden here? The term hidden refers to the fact that POS tags are not directly observable, whereas Markov model says that the particular words information is relied on the previous or the following words information. Now, here we are hiding the POS tags when we are trying to predict the POS tag of the current word and also the previous words. So, we only see the words, those are all nothing but observable symbols, and we must infer that POS tags using the HMM. So, HMM finds the most likely sequence of POS tags that could produce the observed sequence of words. For example, when we take the transition probability, let's say John can see will. So, now how many times noun is being followed by a modal verb and modal verb by a verb by a noun. So, this kind of transition between the tags are identified by transition probability. Whereas emission probability identifies how many times John occurs as a noun and can occurs as a verb, right? Will occurs as a noun is identified by emission probability. Now, in this example, we have, let's say, John can see will, we have noun, modal and a verb followed by another noun, okay? There is another noun, okay. So, now to calculate the probability associated with the particular sequence of tags, what we need is now transition probability. So it identifies the likelihood of a particular sequence of tags. For example, how likely is it that a noun followed by a modal, and how likely is that the modal is followed by a verb, and how likely is it that verb is followed by a noun, right? So this likelihood sequence is being identified through transition probability, whereas emission probability identifies the likelihood of each word given its tag. For example, the probability that John is a noun, or identifying can as a modal, see as a verb, will as a noun. This probability is being identified through emission probability. So for accurate tagging, both transition and emission probabilities should be high for the given sequence. So both the probabilities are being utilized when the HMM identifies a particular tag for the particular word. Now let's take multiple sentences. Mary Jane can see Will, Spot will see Mary, will Jane spot Mary, Mary will pat Spot. Now in this particular example, you could see Mary is being used in multiple places but with a category called N, right? And also we have seen will is used as a noun in one place, will is used as a modal verb, and another place is also modal verb, in another place is also modal verb, right? So now you could see there is a difference in the category identification, right? So now in the previous example, as we said, Mary appears 4 times as a noun. So now what we are trying to do is we are trying to calculate the emission probabilities. So now emission probability says that Mary as a noun occurs 4 times, but will as a noun occurred 1 time but as a modal verb 3 times. Similarly for the other words in the sentence, right? So now how to normalize the emission probability? Now we divide each column by the total number of appearances for that pure tag. For example, noun appears 9 times in the text. Now we divide each value in the noun by column with the noun by the column 9. So wherever noun is there, it's been kind of divided by 9. So this gives a normalized emission probability of each word. So similarly other categories here. So now to calculate the transition probability, we introduce 2 more additional tasks, that is S in the beginning and E is in the end, right? S is placed at the beginning of each sentence and E is placed at the end of each sentence. Now these tags help us in defining the boundaries of the sentences, and it helps us to manage the transitions between the pure tags. So now there is a S followed by N, N, M, V, V, M, V, N, and end of the thing. So each of the sentences are being identified through S and E in the beginning and also in the end. Now how to calculate the transition probability? So now let's create again a table, fill it with the co-occurrence counts of these tags. Now in the beginning, noun occurred 3 times, right? In the beginning, now modal verb occurred in 1 time in the given text. Similarly, the other co-occurrence counts are being identified. Now in the table, as I just mentioned, yes as a tag followed by a N tag 3 times, so the first entry is 3. Similarly, the modal tag follows yes once, so the entry is 1. The rest of the table is filled in the similar manner. Now what we have to do is we are dividing each of the term in a row by the total number of co-occurrences of the tag. So now the total number of co-occurrence says that modal tag is followed by any other tag 4 times. It can be any other tag. So but out of which, let's say 1 time it is followed or by a noun. So divide each of the element in the 3rd row by 4. So now what we are getting is the occurrence of starting of the sentence with the noun are 4 times and 4 times, but it is identified as a noun 3 times. It identified as a modal verb 1 time, right? So this is a normalized transition probabilities. So these are the respective transition probabilities for the given sentences. Now the question is, how does HMM determine the appropriate sequence of tags of a new sentence using these probabilities? Okay, now let's again get back into this example case. Now you see the modal followed by verb is always seen in the text, right? So in this case, model followed by a verb, the model is can and verb is see, right? Similarly, MV and model is followed by a noun in another place and model is followed by a verb in another place. Now, let's consider the sentence like Bill can spot Mary, right? Now, in this case, let's say we supposed to tag each one of them incorrectly initially. Will as a model and can as a verb, spot as a noun and Mary as a noun. But what we actually want is will as a noun, can as a model, spot as a verb and Mary as a, let's say, noun. Right? Noun, what I mean is proper nouns. Okay. Now, let's say what we got is it is a model, it's a wrong one, it's a model, it's a verb, it's a noun and it's a noun, right? Now, how HMM helps in getting this tag, correct tag, using the transition and the emission probabilities. So, there are 81 possible combinations of the sentence that we can derive from Bill can spot Mary when you look at all the other combinations and co-occurrences. So, now we also got the probabilities here. Okay. Now, how does this help us? Now, what we have to do is we have to delete all the vertices and edges with the probability 0 and also include transition probability. Now, the emission probability here has also zeros, right? Now, whenever we get the 0 probability saying that the, let's say, can as a noun occurs in this particular thing followed by another noun, or can as a noun with another, let's say, verb followed by. So, since this data has a 0 probability, so now we will delete all the vertices and edges with the probability 0 and now add the transition probability on the top of it. Now, the problem is now here the can and also spot. Spot can be a noun and spot can be a verb, right? So, now how to identify which is the best one? So, since it is a model, okay, so and a model verb will be followed by a verb rather than a noun, right? So, we are not using any rules here, right? On the other hand, in the rule based pure tagging, we use all these rules and transformation based rules, so that we are trying to identify which combinations are correct. But in this case, what people uses is something like Viterbi algorithm. Before that, I'll also try to calculate the path 1 where the sentence followed by a noun, model verb followed by a noun, that is spot as a noun, followed by another noun, is the probability is this much. And the path 2 is model verb followed by a verb. Now, the probability is this much. Now, clearly the probability of the second sequence is much higher, right? So, the HMM tags each word in the sentence according to this particular sequence, right? Now, how to optimize this HMM? Because we are traveling to multiple paths, 81 times, 81 different kind of paths we have to select to come up to the 2 paths which are ambiguous, then we are using some kind of optimization. Now, can we again use some other method, something like Viterbi algorithm? So, Viterbi algorithm helps us in optimizing the HMM. So, how is it? So, now it reduces the number of paths from 81 to 2. Now, further optimization helps us, like for example, wherever there are vertex with 2 paths, analyze the 2 mini paths leading to the vertex. So, focus on the path with the lowest probability. Why lowest probability? Because that helps us in identifying whether we need to prune it or not prune it. So, now calculate the probabilities for all the paths leading to the node and remove the edges with lower probability, and nodes with 0 probability have no edges, right? So, now how does that helps? Now, consider the mini path having the lowest probability. Now, the lowest probability here, let's say will can, if we take this particular thing. So, will, whether it is a noun or a model verb or a verb, to identify that one, you see the probability of 0 here, right? So, now just remove that probability. Now what we have is only 2 probabilities, and out of which this will have a 0 probability. So now the occurrence of model followed by a model in this case as a will and can both emission, looking at the emission probability, it is lesser. Now what we have to do is remove all the 0 edges and finally retain the things which have higher probability. Now nodes with 0 probability is another thing. So some nodes may have a probability of 0. So now such nodes have no edges attached. Okay, so all paths to them have 0 probability, so no nodes attached, so no need to travel from that particular tag to or a word to another word with their tag. So this helps us in optimizing this one, and now we end up having only the ambiguity places. So the ambiguity places in these sentences are will, either it is a noun or a modal verb, or spot as a noun or a verb, right? So for that one, people again uses forward algorithm and backward algorithm. So look at the back or look at the front side of the tags and see their transition probabilities and identify them. So forward algorithm actually calculates the probability of an observation sequence given in the model. Look at the probability in the forward direction. So now you could say this is the probability of observing the sequence up to time t and being in the state of I. And whereas backward algorithm calculates the probability of the ending state given the observable sequence. So unlike the forward algorithm, here it goes from 1 plus 1 to the end state given the state I at that particular time is t. Okay, and Viterbi algorithm, as we said, it actually optimizes the HMM so that the most probable sequence of hidden states are being found using this particular algorithm. And Baum-Welch algorithm is another type of algorithm. It also helps in even using iterative process on the data. So it helps us adjusting the transition and the emission probabilities so that it helps us in maximizing the likelihood of the observed data. Okay. However, there are some challenges and limitation of this HMM. So the assumption of Markov property is heavily depend on the current state and also the next previous state, right? So it is not going beyond these 2 states. Now fixed number of states are already defined in HMM. So if you are going for a multiple states, it's difficult. And data sparsity is another problem because we cannot estimate this probability unless we have a good amount of data set. And long range dependencies is another important thing which cannot be achieved because they are struggled by capturing dependencies beyond the immediate previous state. So now to overcome this HMM, now we are going to the second model that is called maximum entropy Markov model. So this MEMM is again a discriminative model, whereas HMM is a generative model. So this discriminative model uses the sequence labeling like again Pearson and NER, and it combines the strength of maximum entropy and both Markov models. So again conditional probability is the most important thing, whereas in HMM it is not a conditional probability. So here the model models the conditional probability of a tag given the previous tag and the current observation. So here it is again it can be used with a feature based thing. So other arbitrary features like suffixes, prefixes, surrounding words, capitalization, all these things are being used as a part of MEMM. So how does this MEMM works? Now again this MEMM is a discriminative model. So you could see there are words given there are tags, and again the emission and transitions are being again identified through the calculations like this. Now the difference between HMM and MEMM are HMM is a generative model as we just told, and MEMM is a discriminative model. So in HMM words are modeled as words are actually observations, right, and they are generated from hidden states. And here the probabilities are identified as likelihood probability and prior probability. So the maximizes the join probability so that we are decoding the tag sequence. Whereas in the maximum entropy Markov model. Directly it models the posterior probability. Okay. So, given the word, what is the tag it's been always attached to, and it discriminates among possible tag sequences given a word sequence. And again it uses the conditional probability and conditioned on the previous tag as well as the current tag. And tagging and flexibility here is, in HMM, the probabilities are obtained by training on a text corpus, whereas in MEMM, it builds the distribution by adding other features like capitalization, hyphens, word endings, startings kind of thing, and it selects the maximum entropy distribution given the future constraints. It is more flexible than HMM because it allows for diverse and non-independent features. So, the difference between the HMM and MEMM, as you could see, HMM looks at the words and hides the tags, and it actually uses the transition and the emission probabilities to identify the probability distribution. But whereas on the other hand, as we could see here in the maximum entropy model, so this is actually there is no hiding situation here. It actually identifies the tags, it identifies that word and the relation between each one of them, as well as the relation between the tag and the tag. So, this is the big difference between MEMM and other thing. Again, there are some disadvantages with MEMM. Label bias problem. So, this label bias problem happens when states with fewer outgoing transitions. That means we have only fewer outgoing transitions, but they are always favored with a particular tag, regardless of overall sequence labeling, right. So, again the context window is very less here. So, now again global context is not been obtained through the MEM kind of model. So, it considers only the current word and the previous tag word. So, to overcome this one, we may need another method. So, because MEM does not account for entire sequence context, so it may lead to suboptimal tagging. Now, the third approach that is being commonly used in POS tagging and NER development is CRF based method. This is called conditional random field. Again, it is similar to MEMM. It is also a discriminative probabilistic model, but it is used, unlike MEMM, not only in the local context, but in the global context, with avoiding the label bias problem, because when it is not locally identified, when it is a global identification, the label problem has been solved. And unlike HMM, of course, it is a generative similar to MEMM. Now, why to use CRF? Now, it's consider the entire sentences when predicting the POS tags. So, it helps us in going for a more accurate and context-aware tagging. It overcomes this label bias problem present in the models like MEMM. So, how does it work? It models the sequence data, again using the conditional probability, where T is the sequence of tags and W is the sequence of words. So, identify the probability of T given W. Now, the model uses features from the entire sequence to determine the most likely tag sequence. So, again feature functions are also being part of CRF. It uses prefix, suffix, capitalization, hyphenation and a beginning, end of the word and the word shape. All these things are being considered under CRF. So, this helps in making the informed decision about the POS tagging or an NER. And the advantage of using this CRF is, as I told, it overcomes the label bias and the global optimization, because it considers the complete sentences rather than making the local decision, and the flexibility, because it can allow us to use any kind of diverse and non-independent features. So, the difference again between MEMM and CRF, as you could see, this is the thing. So, this is being hidden and we are trying to identify, whereas it learns through the whole data, and it is not only the next or data only, it goes to the complete sentence level and identifies the tagging. So, now the conclusion is HMM is a generative model, but that's also useful because it's a simple and very interpretable. But disadvantage is, of course, it can struggle with complex features in languages. as well as the modeling part. And MEMM, it's again a discriminative model, but it model works with a conditional probability, whereas this is a joint probability. And the advantage here is it's a rich, non-independent features, flexible, but it suffers from the label bias because of local normalization. And on the other hand, CRF is a discriminative model. Again, it uses global conditional probability across the entire sequence. So, it overcomes the label bias, handles the entire sequence jointly, so that diverse features are learned better in CRF. The disadvantage of using this one is computationally it is intensive, because it has to go for the whole sequence and try to create more kind of nodes and transitions here, right. So, it's sometimes complex to implement and train. And to summarize this one, these are the kind of algorithms, formulas are being used when we are building the HMM, MEMM and CRF based pure tagging and NER for languages. Thank you.